Okay, so putting it all together, what makes a regression line a good model to predict future values of y given an x value? So think about it. What would make a regression line a good model? Good predictions, right? If your model is good, your predictions are going to be good. If your predictions are going to be good, you're going to have small residuals. Remember, residual is the difference between predicted and actual. So if my model is good, I'm going to have very small residuals because my prediction is going to be very close to my actual. So a good regression line will minimize residuals, have a sum of residuals near zero. So if I add up all of my residuals, they should be close to zero, right? So if I want to minimize the residuals and have a sum of residuals near zero, what I'm actually going to want to do is minimize the sum of the squared residuals. Because think about it, if I was using a model to predict your final exam grade, so I had some sort of linear regression line to predict your final exam grade. Let's say your actual versus your predicted grade. Let's say my model predicted you with an 80 and your actual grade ended up being a 90. So I was off by -10. Well, what if your actual was a 70 and I predicted an 80? I was off by +10, right? When I add up my residuals, I get a sum of 0. Because my negative residuals offset my positive residuals, so it looks like I have a really good model to predict your final exam grade, but in actuality, I just happen to be off the same amount in both directions. So to prevent this from looking like a good model for my residuals to cancel each other out, we need to square them to get rid of the negatives. So when I square these, it'll show you -10 squared is going to be 100, and then +10 squared is going to be 100. So now I can say that I was off by the same amount and my direction doesn't matter. So that's why I'm minimizing the sum of the squared residuals. So my least squares regression line is the line that makes the sum of the squared residuals as small as possible. The line that makes the sum of the squared residuals as small as possible. So see, here's my sum of residuals is equal to 0 because they offset each other, but here the sum of the squared residuals is a different number. So I want to minimize my sum of my squared residuals. Alright, using the technology that we talked about in Desmos, find the least squared regression line of the following data. So Sam found how many hours of sunshine versus how many ice creams were sold at the shop from Monday through Friday. So it looks like our explanatory is hours of sunshine, and our response is the number of ice creams sold. Alright, so let's go to Desmos and put these numbers in. Alright, I'm going to start off by clicking Add, Table. Now I'm going to plug in my X and Y values. So I'm just taking these straight from the packet. So 2, 4, 3, 5, 5, 7, 7, 10, 9, 15. Alright, that's all my data set. Remember, each of these represents data points that we collected. So this first one of 2, 4 represents 2 hours of sunshine and 4 ice creams sold. So that's a piece of data that we collected. Alright, you can see that it's plotting it off here to the side. See it over here? Alright, so remember, to get our least squared regression line, we're going to click in the second one, the 2, and we are going to put y. Remember to click the A, B, C, and click the subscript to put 1. And then I need to do the squiggly line. And all I did to get out of the subscript was press the right arrow on my keyboard. M, X, subscript 1. And then I'm going to put the right arrow to get larger again, plus B. Alright, I'm going to minimize this keyboard and I'll take a look. So I've got my R squared and my R. So it looks like my R, I'm just going to add this on here too so we can talk about the R. The R is 0.9796. 2 words to describe that R. Tell me about the strength and the direction of the correlation. Alright, I hope you said strong, positive. Alright, I'm going to write down what my M is, and I'm going to write down what my B is. So it looks like my M is 1.51829. I'm going to keep the full amount. And my B is 0.304878. Alright. And if you look, it plotted the line. So it did its best to minimize the squared residuals here. So it got as close to all those dots as possible. Alright, so I went ahead and I wrote down the R. I described it as strong, positive, and then here's my M and my B. So I'm able to actually write my least squared regression line. So I start off with y hat because this is a model to predict, right? I'm predicting what the response variable will be. I don't know, my model to predict doesn't know what the actuals are. We only know the input, which is x. So I have a y hat because this is used to predict the y. Y hat is equal to. Now this time, remember, we put the constant first. And we put the constant first in statistics because there could be more and more explanatory variables. There doesn't have to be just one. So as we add explanatory variables, it makes more sense to put the constant first and then add on the variables as we go. So here's my constant, and then plus, my M is positive, plus 1.51829x. So this is my least squared regression line. Let's go ahead and try and interpret the slope and interpret the y-intercept. So, my slope. Let's think about what this represents, right? What's my y per x? Let's take a look. Slope is always a rate, right? Something per something. So my y is ice cream sold per my x is hours of sunshine. Alright, so my M is going to be for every 1 hour of sunshine, I have 0.30, ooh, I was writing my y-intercept. Had me back in algebra mode with that y equals mx plus b. Alright. For every 1 hour of sunshine, we sell an additional 1.5 ice creams. So my interpretation of slope is for every additional hour of sunshine, remember, when I'm interpreting my slope, I'm always going to say my x is 1. For every additional 1 hour of sunshine, the number of ice cream sold increases by 1.51829. I'll say approximately 2 to round it to the nearest ice cream. Alright, so that's my interpretation of my slope. For every additional For every additional hour of sunshine, the number of ice cream sold increases by 1.51829, because that's my slope. Alright, does the y-intercept have any meaning in this one? So I always would imagine for my y-intercept, I'm going to imagine can x be 0? So x is hours of sunshine. Could my hours of sunshine be 0? Yes, definitely. You could have a stormy day, right? So my y-intercept is what happens if x is 0. So I'm going to put my y-intercept down here. If there are no hours of sunshine, we will sell 0.304878 ice creams. Approximately 0. Right? I'm going to round that to the nearest whole number because ice creams are sold in whole numbers. I'm going to say approximately 0. So we define my slope and my y-intercept in my linear regression line. All right, let me know if you have any questions.